Dear students, welcome to my classroom. In previous class, we solved some problems in exercise 9.2, and in this class, we are going to solve remaining problems in that exercise. Mainly in this class, we are going to learn how to construct the tangents to a circle from an external point. So take the first one. Prove that the parallelogram circumscribing a circle is a rhombus. So here the question is, the parallelogram circumscribing a circle is a rhombus. We have to prove this statement. That is, if a circle touches all the sides of a parallelogram from inside of the parallelogram, then the parallelogram is a rhombus. That we have to prove here. Okay. So take a parallelogram ABCD and a circle which touches all the sides of the parallelogram like this. Let the circle touches the sides at P, Q, R, and S respectively, the sides A, B, B, C, C, D, and AD. So now ABCD is a parallelogram. Since the sides of parallelogram touches the circle at P, Q, R, and S respectively, then the lines AB, AD, BC, CD are tangents to this circle, isn't it? Because these lines are touching the circle, so that these four lines are tangents to the circles. Now, we learned that the lengths of tangents drawn from an external point to a circle are equal. So then AP is equal to AS and BP is equal to BQ. Okay, since the lengths of tangents drawn from external point are equal, AP is equal to AS, take it as equation 1, and BP is equal to BQ, take it as equation 2. Similarly, CR equal to CQ and DR equal to DS. So these are the four equations we get. Now, by adding all these equations together, we get AP plus BP plus CR plus DR. That is the sum of the terms on left side is equal to sum of the terms on right side. That is AP plus BP plus CR plus DR is equal to AS plus BQ plus CQ plus DS. Now, by rearranging these terms together, AP plus BP as one term, CR plus DR as one term, AS plus DS as one term, and BQ plus CQ as one term, we get like this. Now, from this figure, we have AP plus BP is equal to AB, isn't it? And also, CR plus DR is equal to CD. AS plus DS is equal to AD, as well as BQ plus CQ is BC. So, substitute these values for these terms. AB plus CD is equal to AS plus DS is AD, BQ plus CQ is BC. But in a parallelogram, we know that opposite sides are equal. That is, AB is equal to CD and AD is equal to BC. So that we can substitute CD in place of AB in place of CD, as well as AD in place of BC, like this. Here CD equal to AB and BC equal to AD. That is, AB plus AB is equal to 2AB and AD plus AD is equal to 2AD. So by cancelling 2 on both sides, we get AB is equal to AD. That is, in this parallelogram, the adjacent sides AB and AD are equal. And we know that if in a parallelogram, the adjacent sides are equal, then it is a rhombus. So that as the adjacent sides of this parallelogram ABCD are equal, then ABCD is a rhombus. So in this way, we prove this statement. So the parallelogram circumscribing a circle is a rhombus. Okay. Now take the fourth one. A triangle ABC is drawn to circumscribe a circle of radius 3 cm such that the segments BD and DC into which BC divided by the point of contact DR of length 9 cm, 3 cm respectively, as shown in adjacent figure. Find the sides AB and AC. This is the question. So here the triangle ABC is circumscribed by the circle with center O, and the segments BD and DC are divided by D, so that BD is equal to 9 centimeters, CD is equal to 3 centimeters. Now we have to find the lengths AB and AC. Okay, so here that the circle touches the sides AB and AC at E and F respectively. That is like E is the point of contact, and also here F is the point of contact. Now we have CE equal to CD because the lengths of tangents here AC and BC and AC are the tangents from A, B and C to this given circle, so that the lengths of tangents are drawn from an external point are equal, so that CD equal to CE is equal to 3 centimeters, as well as BF is equal to BD is equal to 9 centimeters, and we don't know the values of AF and AE. That is the length of tangents drawn from A that we don't know. So let AF is equal to AE is equal to some X. Now AB is equal to AF plus BF. As we take AF as X, then this AF plus BF is equal to X plus BF is 9, X plus 9 centimeters. And similarly, take it as equation 1. AC is the sum of AE and CE, which is equal to AE is X and CE is 3. So X plus 3. Take it as equation 2. And now BC is BD plus DC, and 9 plus 3 is equal to 12 centimeters. Take it as equation 3. Now, by observing this quadrilateral OECD, OE is equal to OD because the OE and OD are the radii of the same circle. Okay, so as well as CD equal to CE because the lengths of tangent drawn from an external point are equal. And also angle E is equal to angle D is equal to 90 because the radius at point of contact is perpendicular to the tangent. So by observing these results, we can say that OECD is a square. Okay, now OECD is a square, so that angle C is equal to 90 degrees because in every angle of a square is 90 degrees. As angle C is 90 degrees, then triangle ABC is a right angle triangle in which angle C is equal to 90 degrees. So then by Pythagoras theorem, we can write AB square of the hypotenuse. AB square is sum of the squares of remaining two sides, that is AC square and BC square. So AB square is equal to AC square plus BC square. Now from 1, 2, 3, we can write AB is equal to X plus 9, AC is equal to X plus 3, BC is equal to 12. So from equation 1, 2 and 3. Now by expanding these terms, we get by using A plus B whole square formula, we have A square is X square plus 2AB is 2 into X into 9, that is 18X, plus B square 9 square is 81. Okay, as well as here also X square plus 6X plus 9 plus 12 square is 144. So by simplifying this equation, we get 18x minus 6x is equal to 144 plus 9, 153. And by transforming 81 to right side, we get minus 81. From this, we can write 18x minus 6x, that is 12x, is equal to 153 minus 81 is equal to 72. So, x is equal to 72 by 12, which is equal to 6. As we got the x value, it is easy to find the sides AB and AC. So AB is, from equation 1, AB is x plus 9, that is 6 plus 9 is equal to 15 centimeters, and AC is x plus 3, that is 6 plus 3 is equal to 9 centimeters. So the lengths of sides AB and AC are 15 centimeter and 9 centimeter respectively. Okay, this is the solution of this question. And take the next one. Draw a circle of radius 6 centimeter. From a point 10 centimeter away from its center, construct the pair of tangents to the circle and measure their lengths. Verify by using Pythagoras theorem. So first we have to draw the circle of radius 6 centimeters. And we have to locate a point 10 centimeters away from the center. As this distance is greater than the radius, the point lies outside the circle. Now we have to construct the pair of tangents from this point which is outside the circle. And after drawing the tangents, we have to measure their lengths, and also we have to verify the Pythagoras theorem. Okay, so let us construct the pair of tangents to the circle of radius 6 centimeters. Okay, so watch carefully. Here I am presenting steps of construction on right side. So first draw a circle with center O and radius 6 centimeters like this. And I am drawing a circle with center O and radius 6 centimeter. Now take a point P outside the circle such that OP is equal to 10 centimeters, because we have to draw the tangents from the point which is 10 centimeter away from center. Now draw the perpendicular bisector to OP. So construct the arcs of equal radii from O and P on both sides of OP. Now by joining these intersection points, we get the perpendicular bisector of OP. And here we are taking the perpendicular bisector as MN, and let MN bisects OP at L. Now taking L as center and LO or LP, which are equal as radius, draw a circle like this. So now let the intersection point of these two circles as A and B, like this. Now after that, join P to A and P to B. That is, draw lines through P and A, also P and B. These are our required tangents. P and PB are our required tangents. Now to verify Pythagoras theorem, join OA as well as OB. Now by measuring the angles at A and B, we can notice that angle A is equal to angle B is equal to 90 degrees. That is, both triangle OAB and triangle OBP are right angle triangles. So by measuring with scale, we can observe that PA is equal to PB is equal to 8 centimeters. So we have to measure with scale. And after that, we have to verify the Pythagoras theorem. So in this figure, we have triangle OAP, and in triangle OAP, OA is the radius of the circle, which is equal to 6 centimeters. And length of tangent PA is 8 centimeters, and the distance OP is 10 centimeters. So we have all the three sides of right angle triangle, and just we have to verify the Pythagoras theorem. That's all. So verification of Pythagoras theorem. So here in triangle OAP, we have OA square plus AP square. OA square is 6 square and AP square is 8 square. 6 square plus 8 square is 36 plus 64, which is equal to 100. And also OP square is 10 square. It is also equal to 100. That is, we have OA square plus AP square is equal to OP square. Hence, Pythagoras theorem is verified. Okay. And take another one, another question. Construct a tangent to a circle of radius 4 centimeter from a point on the concentric circle of radius 6 centimeter and measure its length. Also verify the measurement by actual calculation. So now we have to construct the tangents to a circle of radius 4 centimeters from a point on the concentric circle of radius 6 centimeters. Okay, so let us see how to construct the tangents like this. Okay, so observe carefully. Here also now I am presenting steps of construction on right side of the construction. Okay. So observe carefully. First, I am drawing a circle of radius 4 centimeter and another circle of radius 6 centimeters with same center. And here I am taking center as O. And first I am drawing a circle of radius 4 centimeter as with O as center, and also drawing a circle with 6 centimeter radius. And now take a point P on the circle with radius 6 centimeter and join O and P. Like this. Now, like before problem, draw the perpendicular bisector to OP. That is, by drawing arcs of same radii from O and P on both sides of OP, and by locating the intersection points as M and N, and by joining M and N, we get the perpendicular bisector of OP. And let this perpendicular bisector intersect OP at L. Okay. Now we got the perpendicular bisector MN of OP and take the intersection point as L. Now, taking L as center and LO or LP, which are equal as radius, draw a circle which intersects the circle with radius 4 centimeter at A and B, like this. And now the intersection points of these two circles are A and B. And like previous problem, here also join P to A and P to B. Now these PA and PB are our required tangents. Okay. Now, by measuring with scale, we can observe that PA is equal to PB is equal to 4.5 centimeter approximately. And to verify the measurement by actual calculation, join O to A and B. Now, verification of Pythagoras theorem. In triangle OAP, we have OP square minus OA square is equal to 6 square minus 4 square. OP is 6 because radius of bigger circle, larger circle, and OA is the radius of smaller circle, and OP square minus OA square is 6 square minus 4 square, which is equal to 20. And now by calculation we got AP square is 4.5 square approximately equal to 20. So that OP square minus OA square is equal to AP square. So from that, OA square plus AP square is equal to OP square. So hence Pythagoras theorem is verified again. Okay. And now take another one. Draw a circle with the help of a bangle. Take a point outside the circle. Construct the pair of tangents from this point to the circle and measure them. Write your conclusion. Here, the center of the circle is not given. So just we have to draw circle with the help of a bangle. And after that, by taking a point outside the circle, we have to construct a pair of tangents from the external point. So, but how to construct the tangents without knowing the center of the circle? Okay. So how to locate the center of circle? Do you know? The center of the circle is the intersection point of perpendicular bisectors of its chords. So we have to take two chords to the circle, and by drawing perpendicular perpendicular bisectors to those chords, we get the center. And after getting the center, remaining process is the same. Okay. So take a circle and draw a circle with the help of bangle like this. And after drawing the circle with the help of bangle, draw two chords AB and BC to this circle. So I am drawing two chords AB and BC. And now draw the perpendicular bisectors to both AB and BC. So first draw the perpendicular bisector MN to AB. So I think all of you know that how to draw perpendicular bisector to a line segment. So here we are drawing perpendicular bisector to AB. So by joining these intersection points, we get the perpendicular bisector of AB. So here MN is the perpendicular bisector of AB. And similarly, draw the perpendicular bisector DE to BC. In the same manner, we have to draw the perpendicular bisector to BC. So by drawing arcs of same radii from both B and C on both sides of BC, and by joining the intersection points, we get the perpendicular bisector to BC like this. So it's a very interesting question. Observe carefully. Now, these perpendicular bisectors are intersecting at O, which is the center of the circle. So let the intersection point of these two perpendicular bisectors as O. So this is the intersection point. So O is the center of the circle now. Now remaining process system, take a point outside the circle and join O and P, and by drawing perpendicular bisector to OP, which bisects at T. So now I am drawing perpendicular bisector to OP. Here the process is same like as previous problems. We know that how to construct a pair of tangents from an external point to a circle. Here we are proceeding in the same way. So here RS is the perpendicular bisector of OP. Now let the intersection point of OP and RS as T. Now TO is equal to TP, and by taking T as center and TO or TP as radius, draw a circle, and the circle so drawn is intersecting the first circle at G and H. Okay. Here no specific measurements are given. Now joining by P to G and P to H, we get our required tangents. Okay. Here it is passing through H, not B. Observe that. So here PG and PH are required tangents. And by measuring the lengths PG and PH, we can conclude that PG equal to PH. That is, the lengths of tangents drawn from an external point are equal. Okay. So that is the process of drawing a pair of tangents without knowing the center of the circle. Let us see the next problem. In a right triangle ABC, a circle with a side AB as diameter is drawn to intersect the hypotenuse AC in P. Prove that the tangent to the circle at P bisects the side BC. So here the figure is given. So it's very easy. And in this circle, AB is the diameter of the circle, is drawn intersecting the hypotenuse AC in P. Now, we have to prove that this PQ, the tangent PQ bisects BC. That is, we have to prove BQ is equal to CQ. Okay. So, from this given figure, in this triangle, it is given that angle QPC and angle QCP are equal. So, as these two angles are equal, then the sides opposite to equal angles are also equal. So that we have QP is equal to QC. Okay. Take it as equation 1. And here QP and QB are the tangents drawn from Q, which is the external point to the circle. So lengths of QP and QB are equal because lengths of tangents drawn from an external point are equal. So take it as equation 2. And by observing in these two equations, we can notice that QP is equal to both QB and QC. That is, from these two equations, we can write QB is equal to QC. Okay. And it means that the line PQ bisects BC at Q. Okay. This is the solution of the given problem. And the next problem is, draw a tangent to a given circle with center O from a point R outside the circle. How many tangents can be drawn to the circle from that point? Here also no measurements are given. So just we have to we have to proceed with our own measurements. Okay. So observe carefully. Here also we are drawing two tangents to the circle from external point R. So here is the same process. So no change, no more change at all. So we are taking R outside the circle and joining R and O, and also drawing perpendicular bisector to OR like this. So drawing the pair of tangents is very important. Okay, so you must learn the drawing of construction of pair of tangents. So here, watch carefully. So it's the same process. Now we are drawing a circle with L as center and LR or LO as radius, and mark the intersection points as A and B. Now RA and RB are our required tangents. Okay, this is the process. Okay, students, that's all for today, and let us meet in next class. Until then, see you. Bye.